Okay, thank you very much. So first of all, thanks for the kind invitation. It's great to be here and see so many people I've met before and so many people I only know from the papers. So it's absolutely fantastic. I'll be talking more mathematics than physics. So this is just a little bit of warning. And I'll be trying, we heard the bad things about Alan Kahn's approach by chance. I tried to say that actually it might not be that bad, and actually it would be possibly, merging two things probably would be the good idea. So I try to decrypt what photo is. It's first, well, usually, some people use FODC, first order differential calculus. This is first order differential operators. So that would be about Dirac operator, something like that. So this is roughly the plan. I try to be short and more or less talking about ideas. So what is geometry? So this is something like, we had this by Fedele and Sean, geometry and algebra. And I would say actually that there are two approaches. The mathematical approach to noncommutative geometry and all this is sometimes, it goes down back to, topology. So people working with sister algebras, which are very, very fantastic. And this is, something, that people study, classify, look for actions, quantum groups and all that. And this is how it developed. And this is, the essence of that in a mathematical sense to understand it. But, so this is one side. The second side, very often done by physicists is studying, things from the purely algebraic point of view, when you have the algebras given by the generators and relations, and you basically consider polynomials. And this is in the spirit of approach by Sean, which is very, very fantastic for some classes of algebra. So both Sitarz approach is very good, and the algebraic approach is very good. But when you try to look at the geometry in the classical sense that we learned it in a differential geometry course and we applied for the manifolds, this is something in between. Because whenever you have an orientable manifold, you neither work with the all continuous functions on it, which is the sister algebra, or abundant continuous functions, nor with the algebra of polynomials. I mean, when you work on Rn, on the Minkowski space or on the Euclidean space, you don't usually work with polynomials because polynomials have the bad property that they go to infinity. They go to infinity when you approach infinity. So this is, the geometry is something in between, and this is the, one of the difficult problems, understanding, applying, some of noncommutative geometry and some of these ideas to physics is, to have this grasp of geometry. So classically, you start with manifolds, and you define. We know what are C-infinity functions, and then you go on. You define what is the differential algebra because knowing what are the C-infinity functions, you know how to differentiate them. You can coin things, define things like the exterior derivative, so you have differential algebra. Then you can define what is a metric, Laplace operator, everything. Spin structures, spin C structures, and Dirac operator in the end. And this is the classical path that we know it. Well, and then once you do it, then you can study, for instance, the existence of spin structures, classification of all spin structures for a given manifold, what are the properties of the Dirac operator, everything, that comes to your mind. And actually, this is the result. Now, I mean, whenever you try to mimic these things, for the whatever type of favorite noncommutative algebra you have, there's a difficulty because the things that you know classically, you start with differentiable functions. Now, what are differentiable functions? When you have, say, the quantum spheres, one of the best known things in the noncommutative world are spheres, quantum spheres, Q deformations, and the homogeneous spaces of quantum groups. So, and this is, I mean, yesterday we were just discussing, and there was this mention that there's a list of problems by Mark Riffel, and one of these problems was actually, to see what is a good algebra of functions for a quantum sphere. We know what's a sister algebra, we know what's a polynomial algebra, but it was a good algebra that would be corresponding to the infinity functions on the quantum sphere. So this is one of the problems, one of the outstanding problems that are still not solved. Okay, now what is the significance of differential operators? So the idea of con is to encode the geometry, not the way, you know, it's done classically, something like, you know, classically you start first with the algebra of functions, so you somehow know that the algebra of functions infinity is done something. So how to encode it? And the idea is to start with what he proposed, what's proposed as the first order differential operator. Now, what are the benefits of the first order differential operator? First order differential operator is something that, well, basically you can call it partial derivative or a collection of partial derivatives with some coefficients that could be matricial coefficients, like for the Dirac operator. And with the help of that, I mean, you can define something like the algebra of differentiable functions. So the starting point, I mean, which in a classical thing is the sort of one of the final points, is that you work with some Hilbert space. Why working with a Hilbert space? Of course, for finite dimensional algebras or for some truncation, something, it doesn't really matter. I mean, all the spaces you work with are basically finite dimensional means Hilbert. I mean, you need to have, you know, product define it. But generally, the idea of working on a separable Hilbert space is that in the end, you want to employ the tools of functional analysis. So to compute things, I mean, this might be crucial. Now, if you have this first order differential operator, you can reconstruct a lot of things. So first thing is the differential calculus, which is this formula that was mentioned also by Shan, you know, that you, and by Fedele, that you can define the differentials, like the first order differentials, by the commutators. And of course, you know, this trick to tell that you have this operator to be first order, you say that this is bounded. But of course, bounded and boundedness of this commutator is not sufficient. And this is actually a point that links, you know, that would link, you know, to the things that Shan was talking about. If you start with the differential calculus, one usually starts with the differential calculi with a very good property. And this property is, for instance, that you assume that this first order differential calculus is, say, free or projective, finitely generated projective left or right module over the algebra itself. So these are regular. Now you can ask yourself the question, which is very easy question. Assume you take an algebra of C infinity functions on a manifold. So assume you know it. And you take an operator such that dA is bounded. So you represent it on a Hilbert space, you take an operator on this Hilbert space and take this operator that this dA is bounded. Is this D first order differential operator? And the answer is, of course, no. Because you can work as well with the pseudo-differential operators. So it means, I mean, it would include the operators of zero and negative order. And having that, I mean, you would have a large class of objects that only, you know, that are pseudo-differential operators, you know, that the principal part is the operator of the first order. But if you want to say, if you want to restrict further, you know, this operator, if you demand that this first order differential calculus is actually a projective module, then you're back to really first order differential operators. So there's a link. So, you know, it is demanding a little bit more that you demand some very nice algebraic property of the calculus you create that actually tells you that this is a first order differential operator. So there's a significance in working with this. Okay, and then you reconstruct the things, and actually it would matter also, you know, for the definition, standard definition of the Monch-Kantorovich, or somebody say Kohn, or in the early days it would use Gawęcki metric, but anyway, the metric on the space of states, which is very nice because it allows you, you know, to also, you know, define the distance between the spaces and the quantization using generalization of Gromov-Hausdorff distance and connections and everything. You know, and this is, you know, the things that are important for physics. whenever you have this Dirac operator, you can define something like the fluctuations just by adding some connections, and then you put the meaning, to those connections as the physical fields. And you can tell a lot of things like the dimension, the action, spectral action, and we will come to that later on. So this is the way to reconstruct geometry, and I would like to stress, that this sort of significant role is played by something which is called a first-order differential operator. And there's a question, how do we define it? How can we abstractly define what is a first-order differential operator? Not using, you can use this thing that this commutator is bounded, and you can use the condition that this is a projective module. But that's, the feeling was that slightly maybe it should be a little bit too restrictive, or, not very good definition. So what can we replace it with and just get maybe, this projectivity of finitely generated projective module as a result. So this is the idea of original idea of an encount, what is a spectral triple, which is basically a collection of data, an algebra represented on a Hilbert space, an operator satisfying certain conditions, again, that this commutator is bounded, that the resolvent is compact, so in case, you just forget that there could be a zero in the spectrum, that the inverse is compact. Then there are conditions that are basically, the decorations, that you have some gradings, additional grading, Z2 grading, that, has certain properties with respect to the algebra. It commutes with the algebra and anti-commutes with the Dirac operator. And what was introduced, not in the very, very beginning, but later on, and basically the motivation was also to fix, things for the standard model, so there's a physics part in it, was the reality structure. And this reality structure is a sort of thing that appeared, well, one can say out of the blue, but I would try to argue that there's some sort of very good meaning in it. So formulating like that there's an operator with anti-linear isometry, satisfying certain relations that are not very that important, with respect to the Z2 grading and the Dirac operator, so commutator or commuting or anti-commuting with them. The two things are important. The first is the so-called zero-order condition, that the conjugation by J maps the algebra itself into its commutant. And the commutant, of course, is always taken with respect to the Hilbert space. So the Hilbert space is given, the representation is given, so this is the commutant with respect to this representation on the Hilbert space. And this is important because, changing the Hilbert space, of course, changes the commutant. So making the Hilbert space bigger, so doubling the representation, makes the commutant bigger. And so there was the first order condition, zero order condition, so-called, and the so-called first order condition. And this first order condition, mysterious though it is, tells you one little thing, that the one forms, the zero order condition tells you, this J maps the algebra elements, so pi of A maps it to the commutant, so this always commutes. So it tells you that not only the elements of algebra commute with the commutant, this is by definition so, but also the one forms should commute as operators on a Hilbert space. I should put pi here, of course, it should be d pi of A, commute with the commutant. So this is the first order condition. I will also mention, things like the extension of the first order condition and the interpretation of this first order condition, and I will mention, the extension, which was coined by Latham, that's the so-called second order condition. Okay, there are more conditions. If you read the things about spectral triples, there are more and more conditions, which make sense, and basically their sort of way of thinking is adapt everything as much as possible to the classical case. Sometimes it's possible, sometimes not, but that was the attempt. Now, of course, this is all modeled on the geometry that we know. This is modeled on the spin geometry. So whenever you have a spin manifold, and you take the genuine Dirac operator, you take the sin-infinity algebra of functions, you fix a matrix. So you fix the basically also the Hilbert space. You fix the torsion-free connection. You leave the connection to the spinel bundle. So you have a spinel bundle. You have to leave it to the spinel bundle. Then you create the Dirac operator, and then you know that everything of that is satisfied. So that was the basic idea. But well, this is the historical remark that they already said that was proposed for the standard model. But you may ask a question. Okay, the classical example is very fine, but are there any other examples? And there's a list of examples. But well, I think I will try to show the examples here. So first, the sort of ubiquitous example of the noncommutative geometry, which is the noncommutative torus, with the usual Dirac operator. That was the first noncommutative example. Then the finite matrix algebras. Originally, for the standard model, it was adapted to the 3-case, but it could be generalized to any finite matrix algebras. And of course, the Dirac operator is a finite matrix, but you can find some rules and some ways to construct for a finite direct sum of matrix algebras, a genuine Dirac operator, a genuine real spectral triple satisfying all the axioms. Then there were isospectral deformations, so-called theta deformations. First, you can do it. So it's actually modeled on the noncommutative torus. Noncommutative torus is also a deformation of this type, but that was done noncommutative torus somehow like a little bit boring, maybe. So it was done for the theta spheres, so for the deformation of spheres. But basically, whenever you have the action of the torus on something, on some manifold, you can deform it that way. And that was later described very nicely by Alain Kohn and Michel de Bois-Violette in their paper. And finally, there were the Moyal deformation described. Moyal deformation is sort of similar to the theta deformation in some sense. And then the only difference is the Moyal deformation is when you look at it, and it was approached like that as deformation of a plane, or in a higher dimension like hyperplane. So it's not compact, but only locally compact, and that was the first sort of example, non-trivial example, when you can make it with the locally compact space. So deform it, the Moyal, and construct the spectral triple. But surprisingly, when you look at the Moyal from the other angle, this is sort of a side remark, you may look at the Moyal from the other angle. If you look for the sister algebra of Moyal, so you look on the definition of the Moyal, not done by the, so to say, generators like X and Y for the Moyal plane, but you look really for this sort of oscillatory integral definition for the Schwartz functions and then complete it, then the sister algebra of Moyal is compact operators. Well, you can unitize it and add a unit, and if you add a unit, this is unit adding to the compact operators. And as a sister algebra, this is nothing else than the sister algebra of a Podley sphere, the usual standard Podley sphere. So there was an idea, and that you can actually make out of Moyal a sphere, and you can treat the unitized Moyal as a sphere, and you can find the sort of Dirac operator. Actually, we did it for the Laplace operator that gives the constant scalar curvature. Anyway, so this is for the Moyal deformation, and last not least, there's a world of Q deformation, so quantum spaces like SUQ2 and all the homogeneous spaces and the higher dimensional quantum groups, and also the homogeneous spaces, and then a family of Dirac operators, family of spectral triples were found, starting with the Podley sphere, SUQ2, then Planck manifolds, and then other things. Okay, so there's a list of examples, and there's a warning how to construct them. There's nothing. There's no genuine principle how to construct it. But this is, and here, Sham's remark, that whenever you try to do it algebraically, I mean, there's a sort of way. I mean, you start with the differential calculus. So it's very good, but first, for instance, I mean, you need to know the differential calculi and classify the differential calculi, or choose your favorite differential calculus. So the sort of level of difficulty is the same. Okay, now, what is the basic principle of, you know, this, all the spectral tuples and all this, is actually, I mean, one can reformulate the problem in classically. I mean, it's like classifying the spin structures. So whenever you have a manifold, well, you know what is a spin structure, and how to classify a spin structure, but in the noncommutative geometry, I mean, this real spectral tuples give you something like the equivalence classes, I mean, like the representatives of the equivalence classes for the different spin structures. And that's been started by Mario Pashkin and myself some time ago, when we classify, for instance, so this is the tool to study something like the noncommutative spin structures. We classify that for the noncommutative torus there are 4, and that's been later generalized by Yannick Sevensela for the higher dimensional noncommutative tori, that you get the classification, what are the equivalent classes of, well, there was equivariant real spectral tuples for the noncommutative tori. So this is another sound remark. Well, this choice of the spin structure, so actually this reality operator J corresponds to this choice of the spin structure. So again, you can view this reality operator, you can view this piece of construction of the real spectral tuple as something that corresponds to the spin structure, to giving the spin structure for the manifold. And that's, again, you know, as I said, you know, been studied by Yannick Sevensela to noncommutative tori. But noncommutative tori are a little bit boring. So at one point, I mean, I had the idea to look for something more complicated, something which is slightly more complicated than noncommutative tori, are a quotient of the noncommutative tori. And of course, in dimension 2, you cannot do anything. Well, you can, but you don't get, classically, you can quotient torus by Z2, Z3, Z4, and Z6, and Z2 cross Z2, but classically, what you get, so this is for the 3 toric, but classically, I mean, for instance, if you quotient the torus by the Z2, you don't get a manifold, you get an orbifold. This is also one of the interesting questions. Does it happen in a noncommutative case? And funnily enough, I mean, both the concept approach as well as the algebraic approach, purely based on the differential calculus for these objects, and this is, that's, you know, one of the results of work with Tomek Brzezinski, suggests that you have some sort of regularizing. So when you go non-commutative, something which classically is an orbifold behaves much better. And this is actually, and this is quite an interesting point, comes both from the algebraic, so purely algebraic study of the differential calculus and the structure of the differential calculus over this object, as well as from the concept approach. So there's, you know, there's a non-empty intersection. There's something that's happening. Okay, so for the Bieberbach manifolds and Bieberbach manifolds for the 3-dimensional case, I mean, they are genuine, also classically genuine manifolds, and so we were able to obtain the classification of the spin structures over there using the non-commutative tools, both classically and, you know, for the non-commutative case. Okay, so for the length spaces, that was done with Yannick Sevensela. Okay, but now these are the examples. But there's if you look at it, if you look at these examples, there's something, you know, strange. So they are either flat, so something like tori, non-commutative tori with the equivariant Dirac operators, equivariant, everything equivariant. So the action of U1 cross U1 is, you know, is genuine symmetry of everything. Same for the moyal. Moyal, basically, I mean, you have something like version of translations you can have. So this is the picture for some of the things. They're flat. Even the quotients are flat, because what you quotient a flat manifold, you get a flat manifold. And for the spheres, for the SUQ2, for these polyspheres, you require, or you work with things that are symmetric with respect to the deformation of the usual rotational, so SUQ2 symmetry. So they are either flat or round, so very, very symmetric. And those Dirac operators, those geometries that were constructed, were of this type. Now the question is, I mean, this is something strange. I mean, of course, I mean, you can argue that whenever you go non-commutative, you have, your possibilities are restricted. And that was the, for instance, argument of Shannon, that when you go metric needs to be central. So when you go non-commutative, it needs to be central. And for many, many algebras, central means, well, constant. It simply means that the only central elements in many, many non-commutative algebras are just complex numbers. So the question is, I mean, is it the end of the story? Is it the end of the picture? Or can one go beyond it? So can one really have something like dynamical metrics or dynamical Dirac operators, speaking it the other way, for the non-commutative spaces? Now, of course, there are two solutions of that. So, of course, I mean, when one knows, I mean, it could be, well, I wouldn't say proven, but demonstrated that for many cases, I mean, we will break, those axioms. And in many cases, you actually do break the axioms. So, for instance, for the SUQ2, whenever you start looking for the equivariant Dirac operator that would be good for the algebra and satisfy all the rules, you have something like a no-go theorem. So the answer is, and the solution is, you relax some of the axioms. And that was proposed some time ago, that the way to relax the axioms is, that you don't, well, you replace 0 by epsilon. And of course, so this is saying that, yeah, I mean, we have some conditions that something should be 0. But equally well, we say it could be small, very, very small, arbitrarily small. And there's a very nice notion, whenever you work with Hilbert spaces and representations, there's a very nice notion what small is, in a sense. It means you require that this is a compact operator. So that was the original idea for the study of quantum spaces, where this actually happens, and for family of polyspheres, not the standard one, but the other ones, and for the SUQ2 alone, the solution was to relax those things and just say that, well, we don't really need that first order, 0 order condition to be 0, and the first order condition to be 0. We just require it always to be in some ideal of compact operators. And in those cases, there was a very, very small ideal. There was an ideal that you can say, is generated by q is less than 1, by the operator that has q to some powers, I mean, to the increasing powers on the diagonal. So very, very small operator. I mean, actually, the inverse of that is trace class. So in sense, I mean, it was very small. Okay, what's the benefit of that? One was able to create the Dirac operators, create a spectral geometry satisfying somehow these relaxed axioms, and use the tools, for instance, to compute the cyclic cohomology using the Kohn-Moskowitz local index theorem. So this is actually where these tools were. You can do some analysis using those tools, and it was possible to do the analysis in this sense. So compute explicitly using Kohn-Moskowitz formula the explicit cyclic cocycle. Now, they are acceptable, but lead to non-trivial cases in the classical geometry. So you might just think, okay, very nice. What happens if I apply this principle not to the quantum spaces, so Q deformation, but say to the sphere alone? And I asked this question and answered it, that then you get some non-trivial, non-classical geometries. What does it mean in the sense non-classical? For instance, on a sphere, what's a Dirac operator on a sphere, what's the spinor band on the sphere. And generally, well, this is you can see sum of plus and minus, monopole bundles. But you can modify it, you can take the n and minus n monopole bundles, line bundles, take a sum of them, and create a Dirac operator which is, well, also equivariant, basically, I mean, similar construction. Why doesn't it work classically? Because then it actually happens that this, well, the zero order condition is okay, but the first order condition, this thing, fails. So what does it mean? Simply, since the commutant is the algebra itself, because we're working with a commutative algebra, it simply means that this operator D then, for these non-trivial cases, is not a first order differential operator, but a pseudo differential operator. So this is like, you know, something like a softer version of, you know, of spin-off bundle, softer version of the Dirac operator on a sphere. So that's one approach. Second approach is somehow motivated by studies of different generalizations of Dirac operators. And this is, again, you know, there are two things that I want to mention. First is the study of U1 bundles. So there's a classical problem that whenever, and this is a classical problem whenever you have, for instance, I mean, also the SU2 and the S2. This is, so SU2 is the U1 bundle over S2. And this generally, you know, U1 or circle bundles are quite well known and quite well studied. But it's a classical problem. Well, whenever you have a geometry, so whenever you have a metric on total space, it gives you, by projection, and which is equivariant with respect to this U1 action, you can project it and you have a metric on a base space. And then there's a question, can you relate the metric on a top space with a construction of metric on a base space and a connection? And the answer is yes. There's equivalence. I mean, you can express the metric on a total space, which is equivalent with respect to the metric on a base space and the U1 connection. Very nice. But can one do it for the Dirac operator? And the answer for that was given in a sort of classical differential geometry paper by Bernd Hamann and Christian Beer, two experts on Dirac operators, classical Dirac operators, and, you know, provided the answer. Now the question is, can one do it non-commutatively? So non-commutatively, one knows there's a very nice theory of U1 bundles, non-commutative U1 bundles. So generally, you know, non-commutative principal bundles have Galois extension. There's a notion of algebraic notion of connections. So having that, can one actually repeat sort of the reconstruction of the full Dirac operator using the Dirac operator on the base space and the connection? And that was done by Ludwig Nowrowski and myself. And, well, we had a very nice family of Dirac operators, which probably will be on the next slide, which are slightly different than the Dirac operators constructed so far. And this actually, you know, relates to another thing that was studied, well, in the recent 10 years or so, which was a family of conformally rescaled Dirac operators. And the idea is that whenever you have a Dirac operator, you can somehow conformally rescale it. Classically, it means multiply both sides by a function, so HDH or H squared. So, or you can do it with the Laplace operator. So if you take, roughly speaking, D squared as a sort of Laplace operator, then you can rescale it by H squared. That's, of course, this is not the square of that, but up to things of lower order it is. And that was the idea is quite owned by Kohn and Tretkov, and then it was studied later on by many people, Masoud Kalkali and his group, and Ludwig Nowrowski and myself. The only thing is that what we propose is a different version of what was done, namely that we propose that this H to modify the Dirac operator comes from the commutant. Why? Simply because then automatically if D has bounded commutators, then this DH also has bounded commutators. And this is, you know, this sort of, maybe I just, you know, flashed it, this version of the Dirac operator that comes from the sort of another version, which is motivated, again, partially also by this new family of Dirac operators from the U1 bundles, when you make this sort of partial partial modification of the Dirac operator, so only part of the Dirac operator is modified. So for instance, for a torus, I mean, you have two derivations and only one is somehow conformally rescaled. Okay, so these are the examples, and as it was argued, I mean, we need to study by examples, because the examples, I mean, motivate and give us the insight of what should be it's not God's given. I mean, we need to study examples. So what these examples actually suggest? It suggests that you need to change the idea of what is the first order differential operator and the reality. And this is the proposition for some class, not for all of them. At least it works quite nicely for some Q spaces, and it works quite nicely for the family of conformally rescaled Dirac operators. A version of reality which is twisted by an automorphism. Sorry. So the idea is the following. So we have an algebra represented on a vector space, which in the end is a Hilbert space, but you can formulate it, you know, algebraically in this way. And we have an homomorphism of this vector space, which we assume that it defines an algebra automorphism just by composition with the representation. So for any operator, we just compose it with nu and nu inverse. So and this defines automorphism of the original algebra that you have. That's then you can use it, you know, to define and sort of twist the representation by this automorphism. So this is, in other words, you can just say that you use this automorphism to have a new representation, which you call P nu. Okay, and then a definition of a twisted real spectral tuple is just an extra piece of data. It's a spectral tuple with this extra automorphism that satisfies certain conditions. And these conditions are, so you have reality map as it used to be, so J, that maps to the commutant. It's fine. But the only thing is that what replaces the usual first order condition is a version of a twisted first order condition. So you say that these one forms do not commute with the commutant, but twisted commute. So you need to apply those automorphisms. So you see, I mean, on the right-hand side, there's pi of b, and here, this is this automorphism applied to pi of b, and this is in a commutant. This is in a commutant, this is in a commutant, but they are not the same elements. So instead of taking the usual first order condition, you take a twisted first order condition. And there are some other relations that you need to satisfy. For instance, I mean, there's a compatibility condition between dj and this automorphism nu. So dj nu is plus or minus epsilon nu jd. And there's a compatibility condition between j and nu alone, which is j, nu j nu is j. Okay, so this is the definition. And now, of course, I mean, you can put whatever definition you want, but you need to make sure that this definition is not empty. So there's a question. Okay, I mean, I forgot to say, I mean, that if you have grading, that this grading needs to commute with nu square and so on and so forth. But there's a question, is this definition non-empty? So, and does it actually lead to something? So can you do the same things as in the case of spectral tuples? So the first thing is that you can modify the Dirac operator exactly the same way as you can do for the real spectral tuples. So you can add connections. So you can add one forms to make out of single Dirac operator a family of Dirac operator, which is called fluctuation of the Dirac operators. And basically, I mean, what you do, you define the bimodal of one forms to be just, you know, generated by the commutators. And if you modify the Dirac operator by adding this one form and adding, classically you add the one form and its image in the commutant, here you added the image in the commutant which is twisted. And then you can show that this works pretty nice. So whenever you start with a Dirac operator, you can get an entire family of nice Dirac operators. and that these operators will satisfy exactly the same conditions as the original one. So you repeat, in a sense, I mean, all these constructions. So this is like creating a gauge theory for these twisted spectral triples. So a gauge theory for these twisted spectral triples looks more or less the same. Okay, and I skip, the proof and of the theorem because this is just technical. Now the question is, I mean, a single example where it works, and a single example where it works are just this conformal deformation. We actually, in a paper, I mean, I will give the references at the very end. We have 2 examples now. There are more examples. The second example is from the Q-deformed world. But this is the example of conformal perturbation. So whenever you start with the usual spectral triple, you take an element of the algebra. So I take it already in the representation. Well, you take it positive, invertible bounded, K inverse is also bounded, and you take the image of this K by the adjoint action of J, which is in the commutant. And then what do you define? You define the conformal rescale Dirac operator as Kj dk, and you define, and look at it, this is K inverse and Kj, acting on a, say, vector on the space, so a vector in the Hilbert space, a spinor. And if you look at it, well, you can easily see what happens for the commutative algebras. For commutative algebras, Kj is K. So if Kj is K, so for commutative algebras, this is identity. So for commutative algebras, you can rescale the Dirac operator, and this automorphism is just the identity. But for non-commutative algebras, like non-commutative tori, whatever matrix algebras, whatever quantum spaces, this works pretty nice. So this is a way to get non-trivial examples. And then you can show that, well, this is the action of the automorphism of the algebra, and then one can show that this operator satisfies this twisted first order condition, and this compatibility between nu j and nu j and d are actually satisfied. So everything works nice. So this is a class of examples of what one can call spectral geometries, which do not satisfy the usual axioms of Kohn, but they do satisfy modified version. So this is, it's not the final answer, but this is a sort of a way of showing that there's much more freedom, but of course this freedom needs to be explored. Okay. So this is this conformal perturbation. Okay. And the last thing I want to say is a remark on another version of twisting. So there was basically at the same time or slightly earlier when we started working on that, and basically, I would say maybe in the final remarks what motivated the work. There was a paper by Gianni Lani, who will be here, I guess, I mean, in the next days, and Pier Martinetti, about twisted spectral triples and twisted first order conditions for the twisted spectral triples. And they had an example as well. And we started to think, what is the relation? And then we devised one thing, a version of so-called Neuro twisted spectral triples, whenever you have where you have a spectral triple where both the commutators are twisted by one automorphism of the algebra, and the twisted first order condition. So this should be B0, so this is in the commutant. This B should be in the commutant, sorry, so Bj or B0, where they are twisted by some other automorphism, which is actually a composition of nu with this rho. And actually, all the examples that we know fall into this class. So the new identity type spectral triple, which is the untwisted with twisted reality, this is the spectral triple that we considered. And if you take one row, so depending on the extreme cases, one row type twisted real spectral triple is this one of Gianni Landi and Pier Martinetti. So this is a generalization that encompasses both. However, the most important thing is that, and this is the theorem that we've shown, that you can always untwist one of the things. So basically, what we've shown that you can untwist this commutator relation, and I mean the statement is that whenever you start with the Neuro twisted spectral triple, then you can always get the spectral triple of the type some other new identity. So the commutators, so here in these things, you can always make this row to be identity. So you back to spectral tuples. With twisted reality, but you back to spectral tuples. Why this is important? Because the commutators are quite nice for the Fredholm module picture of things. So in the Fredholm module picture of things and for the computation of cyclic cohomology and all that, then the commutators are really more important. Okay, so to summarize this part, so these are, for instance, the examples of what you can do. So if you have K, an element of the algebra, you start with the usual spectral tuple. K prime is in the commutant. So whenever you modify the Dirac operator like that, this new is something like that, and you get this new twisted real structure. So the usual spectral tuple with new twisted first order condition. If you modify the Dirac operator like that, then you get real row twisted spectral tuple. So this is row twisted spectral tuple with untwisted first order condition. And whenever you define the Dirac operator like that, you get twisted spectral tuple with twisted real condition. And basically, you can pass between all these things. So this is the sort of the image that one can have in the back of your head. Okay, any conclusions? I think that would be a good point. But we're still, looking for more examples, to study. One of the examples that we studied is actually very, very simple. 2 points. That was also what Sean was telling about. 2 points. So example of an algebra over 2 points is just C plus C. Still, you have non-trivial automorphism, which is a flip, and still you can represent it non-trivially on a Hilbert space, and you can study what is the twisted version of geometry there. Now there's a good question. There's a notion also of something which are modular spectral tuples and modular Fredholm modules, and this is something we're exploring right now. And something I should also mention, the implications for the geometry, as most of the examples that one studies for the quantum deformations or for the something like quantum spaces or even noncommutative tori are deformations of the usual manifolds. And some of these deformations are along Poisson structure. So there's a good question, what implication it has for the Poisson structure. And this was the original motivation. Namely, there was a paper by Eli Hawking about the rigidity, of deformation, when he was saying, okay, assume that there's a deformation along a Poisson structure, and there's a real spectral tuple that comes for this deformation, the form space. And then he was showing that, okay, there's some sort of no-go theorem, well, for the deformation of arbitrary Poisson structure. So that was the motivation. Okay, yeah, there's no-go theorem, but on the other hand, one should be able to deform things and make geometry rigid. So that was partially the answer that, and that was the motivation when we started to work with on this thing. And maybe this is the good question: was the largest class of conditions that's possible? So how to explore the examples that haven't been yet explored. So thank you very much, and that's the basic references for the thing. Thank you.